There are three main processes involved in first-generation quantum repeaters. Elementary entanglement generation, or EEG, which is used to distribute entanglement between nearby devices. Note that for local area quantum networks, we don't need repeaters or the other scaling technologies we mentioned. We could solely use EEG for our entanglement distribution needs. Entanglement swapping, which is used to extend the distance of the entanglement distributed by EEG. Using swapping and EEG together will allow us to distribute entanglement across far distances. And entanglement purification, sometimes known as entanglement distillation, which is used to ensure that the quality or fidelity of the entanglement stays high enough throughout the entanglement distribution process so that it's actually able to be used for end-user applications. The first step we will discuss is elementary entanglement generation. In EEG, we distribute entanglement between nearby quantum nodes. There are many protocols and even families of protocols for doing EEG. The example shown in the graphic here depicts a meet-in-the-middle scheme. At a high level, and I'm going to leave out some of the nitty-gritty details for clarity's sake, in this scheme, we entangle a photonic qubit to a local qubit on each of the two devices. We then send the photonic qubit from each device to a Bell state measurement station. When we perform a Bell state measurement on the two photonic qubits, the two qubits that stayed on the original devices become entangled to one another, and the qubits that were measured are essentially now classical bits and are no longer to be used. Another common type of scheme for EEG is that of midpoint source, where an entangled pair is created at a single midpoint, such as a nonlinear crystal, and each of these entangled qubits is transmitted to the desired nearby nodes. The next step we will discuss is entanglement swapping. In entanglement swapping, we essentially glue together two entangled pairs to create a longer distance entangled pair. In this graphic, we have two entangled pairs, and one qubit from each pair is on the same midpoint node. We measure the two middle qubits in a clever way, again, doing a Bell state measurement, and when we do, the two further apart qubits will become entangled to one another. This process is actually quite similar to the meet-in-the-middle entanglement generation scheme that we just discussed. Using EEG and then swapping will allow us to distribute entanglement across far distances. The final step we will discuss is entanglement purification. In entanglement purification, we use multiple entangled states with lower fidelity to create a single entangled state with higher fidelity. Purification protocols need a certain level of fidelity for each used entangled state. And so, we need to make sure that fidelity has not degraded too much by the time we run purification. Qubits are fragile, and the quality of their quantum information, in this case the fidelity of the entanglement, decays due to noise. Noise refers to many different factors that can cause loss of quantum information, such as environmental factors, manufacturing defects on components, or natural physical processes. To combat noise and keep fidelity at a high enough level so that we can even do purification, and eventually so that we can run our end-user applications, we must use purification many times throughout the entanglement distribution process. And again, like with EEG, there are many different purification protocols that we can use.